Welcome to this next discussion on how to pick the right test. And this is going to be really fundamental as we get more and more tests in your armamentarium. So thinking about how to pick the right test is really crucial. It's also important to think about when you read a journal article, when they tell you what kind of test they did, for you to be able to then work backwards and think about the kinds of things they were testing. So not only can you start with data and pick the right test to analyze that, but starting with a published article and working backwards and really understanding what they did statistically so you can better understand their particular research question. So, as a quick review, let's go ahead and take a look at levels of measurement. And if you'll remember, we looked at nominal and ordinal variables. The N here is for nominal and the O is for ordinal. Nominal are unordered categories, 2 or more categories. And ordinal are, and I'm going to put here 3 to 7 categories, because an interesting thing happens to ordinal variables as soon as they have 8 or more. Now that's an arbitrary cutoff, obviously, but I'm going to go ahead and put that in green. Ordinal 8 plus categories, so that's an O. So technically these are still ordinal variables, but what happens when you get lots and lots of categories, especially if they're in order, which an ordinal variable would be, that variable starts behaving a little bit more like a scale variable, and although we can't technically treat it as scale, we can kind of move it up the ranks a little bit. The other thing that happens, and we've sort of alluded to this a little bit in the past, is what if you have a scale variable? Remember, this is kind of like along units of measure, but it ends up being where the assumptions are not met. So I'm going to go ahead and add that to this category. So assumptions not met. So these two form a group of variables that end up being very good for what, if you got to inferential, these would be non-parametrics statistics. So we don't cover that in this particular class, but if you hear about non-parametric statistics, or you hear about a scale variable where the assumptions weren't met, either equal variances was violated or not normal, then that would be where we would be thinking about this. Let's also quickly review the descriptive statistics, both the graphs and the numbers that we do for each of these variables, because I think it'll help you visualize the inferential statistics as we get to those. So in terms of scale variables, typically we think of a histogram here. I'll try to draw it in color. And for the numbers part, we calculate a mean and a standard deviation. The standard deviation can also be converted then with sample size to standard error. So those are the kinds of things that we calculate for scale variables. In terms of the this middle category, where it's either scale but the assumptions are not met, or it's ordinal with 8 or more categories, then the descriptive statistics there that are often helpful is a box plot and median and interquartile range. Remember, the middle line in the box plot is the median, and the 75th and the 25th percentile are the interquartile range. When we get down here to the nominal with 2 categories and ordinal with 3 to 7, 2 or more, ordinal with 3 to 7, and this is where we often will make bar charts, pie graphs, and we think about the primary measure of location is mode, like which one of those categories is the most common. And we'll actually be learning a lot of the statistics that go down in this area right now. But all of the tests of group means fall in this top row. So they will be up here above this line as we're kind of going across. And that's because we are testing the group means, and so we want to make use of that information. And we have 4 different tests that we've learned so far: a one-sample t-test, a paired t-test, an independent samples t-test, and a one-way ANOVA. So So I'm going to go ahead and put those on this graph here so that you can see how those are related. And so if we have a one sample t-test, then if you remember, that really takes a continuous variable, right? This is a continuous variable, and it compares it to some kind of standard or a reference value. So I'm going to put compare to standard or reference value. So that's going to be this whole entire first column here. So we will find some statistics down here. There are non-parametrics that can do that, but for now we're learning about the one sample t-test. And so we have a variable. It is continuous. And the other variable, I'll put it in quotes because it's not really a variable, is just a reference value. And a typical null hypothesis would be that the mean systolic blood pressure is equal to 120. And then the alternate would be that it is not equal to. Let me draw the assumption. Actually, the assumptions here is normality, and if I was to draw that as a little graph, here I have one group, they're all in one group, and maybe I have them spread out a certain way. Here's the middle of it, and I'm testing whether that is equal to some reference value. That reference value could or could not be where this particular grouping is located, and that just is kind of what it is that we're testing. The next test is a paired samples t-test. And in this case, if you remember, a lot of times it's a pairing within the same person. So I like to think of this as a before and after. The example that we did from the textbook was the same person eating oat bran versus cornflakes, and so we tested the same person in two different testing situations. And so the important thing then to remember about a paired samples t-test is I've got a variable that is continuous, and I have another variable that I measure on each person, and that is continuous as well, and these are the same thing. Like I was measuring the person's LDL when they ate cornflakes, and I was measuring their LDL when they were eating oat bran. It's not like I measure height at the beginning and weight at the end. That doesn't work for a paired samples t-test, so it has to be the same thing. And so my null hypothesis here is that the mean difference is equal to 0. So notice how we have a something is equal to something. We have here a mean difference is equal to specifically 0. Our assumptions again is normality, and if we were to draw that, again, this is our difference. Again, we have some kind of a continuum, and our group is going to fall kind of like a certain spread. Here's going to be a middle, and maybe this is 0 right here, this line. What we're testing is, are we statistically significantly far away from that line? Here we were testing whether we were far away from that line. These two tests, the one sample t-test and the paired samples t-test, are like siblings. Mathematically, they're very similar to each other in that we're testing one group or one difference and comparing that to some number. Here we're automatically comparing it to 0, and here, or usually, I should say not always, but here we're comparing to some reference value. within that one group. After we look at the one sample t-test and the paired samples t-test, then we move on to a couple of more tests, and I'll try to see if I can get them all on the same screen here. The next one is called the independent samples t-test. And here we have two groups. So the defining feature here was a reference value, here was a before and after, and here we have two groups. And so now we don't just have the measurement for one group altogether, but our variables are, we have a continuous variable, and our second variable is what is our grouping variable, and I'm going to call that categorical with two categories, because for an independent samples t-test, by definition there are only two groups. Our null hypothesis is that the mean for group 1 is equal to the mean for group 2, and now we have assumptions of normality and equal variances. And so the way that looks now is that we have group 1 and group 2, and each one of them has a certain spread, and we're wondering if the averages for them are far away from, kind of like this. I didn't draw that very well. Let me put another line in there. Are far away from the overall average. So this is the continuum over here on the left. So that's kind of a visual of that one. And then finally we have a OneWay ANOVA, and this is just like a grown-up independent samples t-test, or another way of saying it is that the independent samples t-test is a specific case of a OneWay ANOVA that only has two groups. So in a OneWay ANOVA we can have three or more groups. Mathematically, it's not wrong to run two groups as a OneWay ANOVA, just independent samples t-test is a better answer for those scenarios. So here we have a variable. We have a continuous variable that we're measuring because we are doing tests of group means, and here's our three group means of our continuous variable. And our other variable that we measure on each person is a categorical variable that has three or more categories. And so if you think about that, that could either be nominal or ordinal that has three or more categories. Our null hypothesis is that mean 1 is equal to mean 2 is equal to mean 3, and so on. Could be mean 4 and 5 and 6. The alternate is important here because it's different than what we've seen in the past. At least one mean is different. And then the assumptions again are normality and equal variances, just like we saw with the one independent samples t-test. These two tests are so similar to each other. The only difference is the independent samples t-test only has two categories, and the OneWay ANOVA can handle three or more categories. So let's go ahead and draw that really quickly. It'll be very similar to what we saw before, only now we have three or more groups, and each one of those has a mean. And what we're wondering again is how far away are those from the grand overall mean. So that's kind of like a visual that goes along with that. So that's a quick overview of all the tests that we learned about and how you would tell the difference. Basically, what you need to do if you're given any kind of a testing scenario and asked to pick the best test is you would be looking here to see what kind of variables do I have. Now the thing that you'll notice is that every single one of these has a continuous variable, and it has to because we are testing group means. We can't test group means if we don't have any means to test. So for a one sample t-test, the other variable is a reference value. For a paired samples t-test, our other variable is the same variable measured, under a different testing scenario, either before and after, or given that you're doing something different. Independent samples t-test, we have basically a dichotomous variable here, a nominal variable with only two categories. And with the OneWay ANOVA, my other variable is a categorical variable with three categories or more. And so that's the way you're going to be able to tell the difference. The other thing I want to point out is, as long as we really only are looking at this one group, we only have the assumption of normality. As soon as we have more than one group, then we need to know if the variances for those more than one group are equal to each other. So we have not only normality, but we also have equal variances. And sometimes people will throw in the assumption of independence to all of the statistical tests for the reasons that we talked about. I could draw this line over quite a bit farther. All of these are non-parametric tests that you can do as a way to evaluate those relationships once you have this situation where the assumptions are not met. So we hopefully that will be helpful to you as you are studying about how to pick the right test.